Thank you all for coming. It is my pleasure to introduce Tamar Avineri from North Carolina School of Science and Mathematics.
Thank you so much, Gavin. Yes, my name is Tamar Avineri. Thank you so much for coming to the session. I'm a math instructor and department chair at the North Carolina School of Science and Math. As Gavin said, we're located in Durham, North Carolina. We're a residential public school serving juniors and seniors in high school. We work hard to incorporate modeling in all of our classes. And the problem we're discussing today is a great example of that. I'm looking forward to spending the next 30 minutes with you. And I always like to present my talks in a way that models what happens in the classroom. So this will be a very interactive session. If you need to grab some paper or take a moment to gather some materials, and I'm going to ask you to work some questions as we move through the presentation. The problem we'll discuss today is the amusement park circulation problem, and it's well placed in any differential equations class. It involves coupled differential equations and eigenvalues and eigenvectors, but it is very accessible. Here we go. So in my classroom, I put students up in groups of 2 to 3, and they work collaboratively towards a final write-up. That they turn one per pair or triplet. This typically takes about 2 to 3 days in the classroom, with their only homework being work on the assignment outside of class during that period. I'll give you a moment to read the problem prompt and give me a signal when you're ready, either with a hand up or something in the chat. I'll be quiet for a moment. So I'd like to take a moment to answer the first question prompt with you. Determine equations modeling how fast the number of visitors in each region is changing with respect to time. Give me a signal when you're ready. I would love it if someone would be willing to take yourself off of mute and describe what thought process you had. Where did you start?
Oh, hello, Tamar.
Yes.
For me, I went with the logic of how much they are losing from each park and how much they are gaining per hour.
I love it.
So I got the 3, and I don't have a paper to write them down, but if you're losing 40% is negative 0.4, the original function, if we're in land of geometry, called g. If they are gaining, plus the whatever percent they have.
Yes, so geometry world is losing how much each hour total?
40%, and they are gaining from the probability 30 and from the function 20. So 0.3 g plus 0.2 g minus 0.4 g, all of them is the dg over dt.
Okay, so we're losing, you see, we just said 40%, but we also have 40% going to function city. So geometry world would actually be losing how much of its current amount?
80.
80, yeah. So we're losing 80%, but you're right, we're gaining 30% of who?
From probability and 20 from function.
Exactly, yeah. So if we think dg dt would involve both what it's losing, as you said, losing 80% of its current amount, but gaining 30% of probability and 20% from function city. Yeah. So will dg dt will it be dependent on the other 2 lands? Will its equation, the differential equation, would it involve just g or also p and f?
Oh no, p and f, definitely.
Yes, yes, yes. And we do we do the same thing with dp dt and df dt. So let's take a look. Okay, so here's the prompt. And there we have the differential equations to compare them to. Any comments up to this point? Is this something you see your students being able to tackle?
Personally, no. I've never had a system of differential equations, but that's fun.
Yeah, and I love that they're coupled. You know, they are dependent on the others, and it makes solving them that much more sweet, sweet and rigorous. All right. Okay, so in order to solve the system, we have to employ the use of eigenvalues and eigenvectors. So it would be, the students would have had some of that background knowledge in addition to just differential equation, modeling differential equations. So here's the system in matrix form. And then you can use a calculation tool. In this case, I've used Wolfram Alpha. We can identify the eigenvalues and eigenvectors and decide where to round to. And then here we use the we apply those values and vectors to our solution template, which would be something I would have covered thoroughly in advance of this project, so they would know to do this next. And then we can use our initial conditions to identify our constants D1, D2, and D3. And in solving our matrix equation to find those values, we see D here, D1, D2, D3. We've decided to round it to the 10th place. So that gives us our specific solution here. We can also write this out in system form. So when we take a look at these equations, is there anything that you notice that allows us to know something about the scenario? Is there something that we can reason through that makes sense, essentially?
The negative exponents?
Negative exponents, nice, yes. And they are consistent. They're all in that sort of template that I call. Yeah, negative exponents. What do you notice about the constants in each? It's sort of a check for reasonability in context. What do you think? Yes. Yes, both Paul, thank you for the direct message, yeah. And Aaron, they add up to 1,000. Scott, that they're positive, you can't have negative number of people. Also, the sum better be 1,000 at all times, exactly. Yes, up to rounding error, we notice that the constants add up to approximately 1,000, which is reasonable. That's exactly what we would have expected. So the limiting distribution of the people of time increases without bound. We also note that it is proportional to the eigenvector associated with lambda equals 0, simply rescaled so that the values do sum up to 1,000. We can also look at this graphically. There are a lot of really rich questions that you can ask students just on interpreting what the graphs give you. This I used Desmos to graph the 3 functions on the same set of axes, which is a really nice way to analyze and compare when they're on the same set of coordinate axes. So this is good work, but it's in context. There must be something that we need this model for. So we always ask questions of students, either very specific questions that does kind of guide the student towards what we're looking for, but sometimes very open-ended, like, give me any thoughts that you have about what you notice with this system. So we notice that all 1,000 visitors begin in geometry land. If we notice the graph, the y-intercept for the red graph, which is geometry land, that starts at 1,000. What else do you notice here? What happens over time? And I can go back. The red graph is G, blue is P, and the green is F. Scott, I see your chat SIR model where nobody dies. Paul, yeah, steady state at around 8 hours. And yeah, Scott, equilibrium, exactly. Same point. Anything else? And when you say equilibrium, Scott, when does it happen? If we think of the y-axis as the opening at 10 a.m., where does it start reaching that equilibrium? Okay. Do you notice in the graph, this is in response to Scott's chat for purposes of the video. Yeah, you'd said infinity, or when the smallest point is less than one person, or the smallest difference. When do you see that sort of occurring in the graph? Where do you see sort of this stabilization in terms of time? So we open at 10 a.m. and things don't really change after when? About 8. Okay. So about 8, so that would be 6 p.m. Right? 8 hours after 10 a.m. Nice. What do you notice about the long term for function city? And what do you think allows us to anticipate this from our differential equations? We'll go back here. There. So if we look at the rates at which people are moving to specific regions in the amusement park, knowing that function cities, that was the green graph. What do we notice is different about df dt that dg dt and dp dt have in common? Okay, yes, so Charlotte, you said negative f. Okay. And the others have, they are receiving from function city. What else? Thank you, Gavin. Yes, Scott. Yeah, that's nice. To solve for the solve for the equilibrium. Yep. What explains what we notice in the graph here? How can we sort of anticipate that from our differential equations? So Leela, you say each coefficient plays a role in determining the magnitude of the decay for each term. Yes. So what do you notice exactly? What do you notice in those coefficients for df dt that's different from dg dt and dp dt? That may explain why we see that attendance in function city kind of reaches far outruns G and P. And exactly on that point, Leela, yeah. And Charlotte, you came up with a good point about a negative F. If we notice how much is leaving, what percentage of the population is leaving function city versus how much is entering function city? Yes. Yes, yes. So I see from Leela, the coefficients control how quickly or slowly the system moves towards zero. And Paul, your point about more people are entering F. than are leaving. But what did we notice about dg/dt and dp/dt? They're losing people at a higher rate than they are gaining. If we look at the coefficients, as Leela said, about negative 0.8 versus 0.5 for dg/dt. So I am losing more in the long run than I am gaining. dp/dt, same issue. I'm losing more than I'm gaining. But at df/dt, we notice we're gaining a lot more than we are losing. Oops, so I've got to go back. And I know I'm close to time. So we have some of those interpretations, and wanted to get a little bit of this out as a conclusion to this problem. Some of the learning outcomes that we set for students to achieve by the end of their differential equations class is to set up and solve simple equations using standard techniques from calculus, like separation of variables. Students will be able to use these techniques to write and solve equations to models for classical situations from physics and other applications. So it's a perfect applied math kind of problem. Recognize when an equation is not solvable by standards or standard techniques, and then be able to implement numerical methods if needed. And then solve modeling problems, particularly open-ended ones. And then effectively communicate the understanding of concepts verbally or in writing, because that's one of our highest priorities for our students, is to communicate their thinking, both verbally and in the written form. We also are very particular, especially the higher the math we teach, higher level. We really are very focused on precise notation and terminology when writing. And then computing eigenvalues and eigenvectors analytically and numerically using technology. Using collaboration to solve problems. So that's why we set students up 2 to 3 or so. And then write mathematical functions and differential equations to model situations described verbally or graphically, both individually and in groups. And then use technology when it's appropriate. You saw I used Wolfram Alpha. That would not be something I would expect my students to do. And it's much less important for them to do that from scratch than to get the constants and then be able to interpret. That's where I like to focus. So thank you so much for coming. I would love to have any questions, see if I can answer them. My information, my email address is there. Our website is also there. And I think there may be an opportunity later, and I'll check with Gavin if these materials can be shared with you all.